Hi everyone. Welcome to the MathSpellBook. Welcome to MathSpellBook. I'm your host Peter, and basically we are going to continue on with our origin of math series here. So I'm going to connect to Sascha on Discord so that we can begin. Hey Sascha, stream is ready for you.
Hello.
Okay, did you get the link for the Excel draw?
Excel draw?
Yeah. Dang, I'm
Yeah.
Okay.
Yeah, it's fine. How are you today?
I'm alright. How are you?
Oh man, I went for a run and didn't well.
Oh, okay.
Yeah, I'm not.
Okay, cool. I can see your thing. Okay, because I actually like unplugged my my modem before just to see if we won't get as much cuttage. So I can see your cursor. So I think we're starting off good. But try writing something. Try writing something so we can see.
All right, I'm gonna do a smiley face.
Yeah, I
we're
see
happy
it.
to-
I see it. I see it.
Oh wait, I can wait. Is that in you? Oh, that's cool.
Oh, what's going on?
So before, when I was using this application, I had to like press the E button on my keyboard to be able to erase. But now I can just use the tip of my, I will say my finger, but it's not my finger, it's my my pen.
Your stylus, yeah, your stylus, yeah.
Yeah. so oh, that's pretty cool.
Nice.
I was kind of getting used to the motion when I was like, to have like one note. I was like writing stuff, and then
the
was
application went
pressing
through an
keys.
update since we last did it.
Yeah, that's cool. I mean, I don't know if they changed it like a week ago or something, but I just realized.
Yeah.
Alright.
Okay, this will make it easier then. All right.
Yeah. So today we have two choices of things that we can do.
Oh, okay.
So we can either apply what we did last time and build a real number for real.
Okay.
Well, that's kind of a funny sentence. Or we can do like a funny exercise about a sequence of rational, which is approaching square root of 2.
I mean, I'm familiar with this proof. Like proving that this square root of 2 is irrational, right?
Well, we're not just going to prove that. We're going to prove that there is actually a sequence of rational which approximate the square root of 2. And that will give us an example of a sequence of rational number which is Cauchy but not converging.
Well, I'll let you decide which one is more fun for you to discuss.
I mean, both are fun. I mean, okay, building the real number is a little bit more abstract. The other is more like concrete, but I don't know. What do you feel like for Wednesday?
Let's see. Last stream was very abstract, so let's go with something more concrete then.
All right.
Something we're familiar with. Something we're familiar with, I guess.
Yeah.
Because we went into ring theory last time.
Okay, so I will have to do a little bit of homework that I haven't done last time. I will have to show you that some sequence converge.
Okay.
So, okay, maybe I will just give you a brief reminder. So recall.
Okay.
So I will recall you the Archimedean properties, okay?
Okay.
I cannot spell this thing, so I'm sorry in advance.
Sorry.
I mean, it's kind of throwing me away. Archimedean? Maybe it's how it's spelled in English, I don't know.
I think that's close enough. Yeah.
Yeah, that's close enough. If you don't look too closely and you're very far from your monitor and your eyes are closed, I think it's fine. Okay. So what it was saying if you have a real number, that's a real number. I mean a rational number. Which is positive.
Yeah.
Okay. Then for every, maybe I will just make sure I don't say garbage. Properties. Oh yeah, okay. So for every x which is bigger than 0, and for all y which is also bigger than 0, so those two guys are rational numbers. Maybe I should put default there, all x and y which are both positive,
Mhm.
then they're gonna exist some natural number n, such that nx will be bigger than y.
Okay.
Okay,
Mhm.
and this was one of the property. I think we showed it 2 stream ago, maybe 3 stream ago even.
Yeah, I think it was the stream before last one that you showed this, I think.
Yeah, and I think, yeah, and one of the application I showed you is that if you have, what was it? I think we had like something like that at some point. The distance between two points, and the
Yes.
distance was less than epsilon for every epsilon. And I say, well, using the Archimedean property, you can conclude that actually x has to be equal to y. I mean, the distance has to be 0.
Mm-hmm.
Yeah. And one of the application of the Archimedean property is for showing the following.
Yes.
So it's gonna be very about the epsilon proof. So I think it's good practice because usually those are the most important proof to mastering real analysis.
Mm-hmm.
So lemma, the sequence an 1 over n is converging to 0. Okay.
Mm-hmm.
So it's kind of funny last time because I showed you like a few ways that you can stitch convergent sequence together. You can add them, you can multiply them.
Yeah.
But we haven't really like proved any meaningful sequence converge. And I will show you why this the convergence of this sequence follow from the Archimedean property.
Yeah, this is usually what you first learn about, like, I think series and sequences. I think like
Yeah.
you go over more in series, right? Where it's like 1 over n is getting closer to 0, but you feel like you know it, but at the same time you always get reminded of it in calculus.
Yeah. And so the way it's gonna work is the
Mhm.
following. So let epsilon be greater than 0.
Greater than 0. Okay.
So we want to show that the an is converging. So maybe I will just restate the goal.
Like, one funny question though, like
Yeah.
for real analysis, is it like basically like your professors are like, if you don't write at the beginning of your proofs, let epsilon be greater than 0, you fail the course? Something
Well,
like that.
usually you have to write it if you want to be like having good etiquette. But sometimes in papers, people just say, "Oh yeah, just take a." I mean, they sometimes I kind of forget to mention that. Oh yeah,
Because like the amount of times that I've seen you write let epsilon be greater than 0, I'm like, oh, this must be like a big thing like in real analysis that you have to get used to. Like let epsilon be greater than 0.
So the goal from that is to be able to find some natural number n bigger than 0, such that for all the rank which are coming after again,
Yep.
we have that. Well, here, okay. If we're very strict about the definition, it's going to be so maybe I can just rewrite it because it's not quite the definition. So usually you will have your sequence minus the thing that your sequence is converging is as an epsilon, but
Oh yeah, the epsilon definition, right?
yeah. As our limit point is 0, then we just get that this is equivalent to 1 over n has to be less or equal to epsilon.
Mm-hmm.
And we can even do it a bit better because we know that 1 over n is always positive, right?
Right.
Therefore, we just have to show that 1 over n is less or equal to
So
epsilon.
epsilon.
Because we don't need, I mean, this quantity is already positive, so the absolute value will do nothing.
And this is basically the scratch work, though, right? Because you just...
Well, this is not really the scratch work. It's just like I just restate the goal.
Oh, okay. Because I thought whenever you wrote goal, this was sort of like, oh, this is the scratch work that... This is like the blueprint of we do before we write the actual proof.
I mean, it's not really scratch work here. I just restate the goals. I just say, well, maybe I would have written like let epsilon be bigger than 0, and then I would have say, well, it's
So-
enough to find some n which verify those properties.
Yeah, I think like the big question I want to ask before we continue is that I know I've probably asked you this before, but how do we know which stuff that we write as how do we know what is really scratch work and what is actually needed in the proof so it's not considered scratch work in it?
Well, I mean, usually scratch work, I mean, at least for analysis, usually what you will do is you will just play with this inequality without like saying what epsilon is, what n is. You just like play and try to get some balance.
Is it mostly like the algebra that is involved, or is it like just like basically just your ideas? Because that's
So, I mean, when you do,
that's what confuses me about like the definition. I mean the distinction between scratch work and the actual proof. Because I know in proof sometimes you do the algebra, but there are times when you don't, and that's considered scratch work in some proofs, and sometimes it's not.
well, I mean, okay, the word scratch proof is kind of scratch work. I mean, it's kind of a loose term.
Yeah.
I mean, it does not really have a meaning. I mean, usually what people will mean when it's scratch work, they mean like either like they don't care about the hypothesis and they just play with the thing they care in the proof. For example, usually in real analysis, it would just be playing with the inequality and stuff like that. Like we did. I mean, I gave you a proof this week where we had to do that.
Mm-hmm.
And usually what you do is once you understand why the proof worked, then you write like a formal statement. Yeah, and here I'm kind of in the middle because I sort of know what's the trick to this proof. So I don't do a scratch work before because I already know like what's gonna happen.
Mm-hmm.
Okay.
All right.
And
go on.
okay, and maybe I'm gonna restate last time this inequality. So what I can do is I can multiply by n from both sides.
Right.
And then we're left with this. Okay.
Uh-huh.
And this looks very familiar to the Archimedean properties. So
Okay.
what we're gonna do is we're gonna do the following.
Mm-hmm.
We're gonna take so by the Archimedean properties. Maybe I will just write the art comme ça, like that. We know there exists some n, which is some natural number,
Okay.
such that, well, I guess we can even have stronger in bound. We can have this, such that we have this.
Okay.
So if you go back to the Archimedean property, what I use, so in the Archimedean property, I have an x and I have a y. Here I specialize to the case where y is equal to 1 and x is equal to my epsilon.
Yeah.
And from that, it's not very complicated because if you have if n is bigger than big N, then as epsilon is positive, maybe if n is bigger than n, and as epsilon is a positive number, we must have that n times epsilon must be smaller than n epsilon. Okay?
Mm-hmm.
Therefore, if you use the bound that we have here, we have that 1 has to be smaller than n epsilon. But from the thing I wrote in red in the goal, this inequality is exactly the same as the one we care above. Right?
Okay.
Therefore, this showed that 1 over n is converging to 0. So maybe I can just, or maybe if you don't want to use the thing I wrote in red, we can just divide by n. Which show that 1 over n is converging to 0. We should complete the proof.
Okay, so like recapping, so we use the definition of the Archimedean property.
Yeah, to be able to find this initial big N, yeah.
So basically all x and y that exist within, in this case, the rationals, x is greater than 0, and all of x is greater than 0. There exists an n within the natural numbers that n times x is greater than y. Okay.
Yeah.
So we have a lemma that basically says that an is equal to 1 over n, which converges to 0. The proof behind that is let epsilon be greater than 0. So the goal here is also part of the proof, right?
Yeah, so basically here I just restate, like, if I'm able to show what's the goal is asking us to show, then we're done.
Would that be in a formal proof? Like basically say, like, let epsilon be greater than 0, and then you just write goal, and then you just write this part? Would that actually be in a proof, or would you have to rewrite that to be more formal in a proof?
So, okay, so it kind of depends to like which person you write this proof. So if I'm writing like for mathematician, I would probably never write the goal because everybody knows the definition of.
So this is like for like this is for like something like a student to read mainly.
Yeah.
Okay.
So basically, I'm saying, well, if we want to show that n is converging, we have to write down what it's mean for it to be converging. So here the goal is more like a reminder, but I mean, if you're talking with people who did like that plenty of time, you don't want to do that because otherwise they will think that you're a very pedantic person.
Oh, okay. So let's see. So we have one that is less than or equal to n epsilon, right? So...
Yeah. This is equivalent to the first bound. Those two guys are. I should probably put if and only if.
With the definition of a limit.
Yeah.
Okay.
Like if you have this, you automatically have the thing on.
Yeah, because basically you just consider it like, oh, it's -0 or something like that.
Yeah.
By the Archimedean. So I think like up to right here, I'm trying to like, I know it's supposed to reflect this part of the Archimedean property.
Yeah.
But at the same time, like, I think what's kind of tripping me up is like, because it's supposed to be n times x is greater than y. So I'm trying to see, is y 1 in this case, or is y supposed to be n?
Yeah, exactly. 1? Yeah. Y is exactly 1.
Okay, so basically y is supposed to represent, I guess, the sequence that we're working with in this case.
So
is n
the
over
one.
1?
So basically, when I rewrite the goal, I found this, right?
Yeah.
And as I said, this really looks like the Archimedean property.
Yeah, I can see it sort of looks like it, but it's just
like
different.
1 and epsilon are both positive, and what would you like to be able to do is to be able to find some n which makes this inequality hold.
Yeah.
So that's why you want to use the Archimedean property.
Mm-hmm.
And
also,
that's what I do like in the next step.
I think I just solved it in my head a little bit. So basically, if you flipped it over and basically made n epsilon is, let's see, this one says less than or equal to, then, oh no, because I'm thinking of the opposite of like, because that wouldn't make sense, because then it basically says, no, it says 1 is less than or equal to. Oh, okay, so it makes sense, yeah. So n multiplied by epsilon is greater than 1, right?
Yeah.
In that case? Oh, okay, it's just flipped over. Oh, okay, because like I know it's something that you would probably see like in algebra. Duh, like that's the sign, like, you know, like like less than or equal to, the opposite is greater than, and I'm like, I know I had to see it somewhere. Okay, I think I see it then. Okay, by the Archimedean principles, such as I know I'm repeating myself a lot, guys, but this is just basically how I can basically turn this into my own personal thoughts, so, you know, bear with me. And maybe
it's fine.
And maybe like me repeating it to myself helps you repeat it in your head too, and maybe you'll be able to think of it in a different way than I do, you know. Okay, so basically n and n, like, I guess they're treated as the same because they're part of the same, they're related to each other, big N and little n, right, in this case?
Yeah.
So like we're sort of treated as the same, but they're just, I guess, like in the proof, like you consider them as different, but yet, like, you know, quote unquote, but they're still considered like the same because like little n is in big N, right?
So little n is bigger than big N.
Oh, little n is bigger than big N.
Yeah.
Okay,
So okay, maybe I can just give you some marks. So so this part
Yeah.
So okay. If we go to our goal,
Yeah.
if we look at our goal, our initial goal is to be able to find some big N, right?
Right.
And what I claim here is that my big N will be the one given by the Archimedean properties. And but I mean, big N. I mean, it's not just enough to have a big number. You want it to satisfy some stuff.
Yeah.
And what it's supposed to satisfy is supposed to satisfy this guy. For all little n which are bigger than n, we should have this inequality at the bottom.
Okay.
And what I do is I just say, okay, let's take n to be bigger than little n to be bigger than big N. Sorry.
Right. Yeah.
And I say, well, I mean, this inequality, if I multiply from both sides from by epsilon, then I get exactly that.
So
I get that.
So like this is bringing me back to what we were discussing with sequences, like, you know, the radius of a sequence. Like, say if we start at the first term, the radius would be very, very far. But if we go closer and closer to numbers bigger than n, basically that will close the radius, making it a much more how should I say, converge onto one single value that actually defines the sequence, or the sum of the sequence, as it were. So is that the same here, where it's like, since little n is bigger than big N, is it sort of like the same type of idea, where it's like we're just trying to shrink it down to the point where it's like we can actually get a number or a value from it? That's my question.
So maybe I can draw you a little picture. I'm not sure if I'm getting the question, but so let's say this is the rational. And here we have the origin.
Yeah.
And then we have our sequence like 1 over n. Okay, so a1 will be 1.
Yeah.
a2 will be 1/2, and so on, right? They're getting like smaller and smaller.
Yeah, they get smaller and smaller, but they get closer and closer to a specific value.
Yeah. And what's
yeah, go on.
And so we have our tolerance, which is epsilon.
Yeah.
Which is maybe we can think of it as
somewhere over there, like whatever, like epsilon is sort of like a parameter.
Yeah. And what's going on in the proof? So first of all, we use the Archimedean property to say that for at least a big N, we're able to find a point. Let's call it maybe a big N, which is inside of this. Maybe I should write it like that. I'm sorry.
Yeah, that's fine.
Which is inside of this epsilon ball.
Which is epsilon.
Yeah. But if we use our sequence, obviously, if like, okay, so maybe this is just like inequality stuff. So if n is bigger than big N, then you can multiply it. Okay, so okay, maybe we can think of them if you flip them. So you flip them like that, then you're gonna have that 1 over n has to be smaller than 1 big N, right? But this guy is still positive, so basically what's gonna happen is the rank which are bigger, let's say maybe little an, they will have to be also stuck inside of this epsilon ball between 0 and an.
Right, so it is the same concept that I was referring to. Okay.
Yeah.
Because I know with epsilon and n and big N, we have to think of it as like sort of shrinking, I guess, the sequence in this case, to basically get us a value that we think is useful. Yeah,
so epsilon is kind of a tolerance, and you want like you want to.
It's like you're basically playing. It's like you're playing with a stereo, old school stereo, and you're just basically turning the dial to get the right sound, the right pitch.
Yeah, I think I'm a little bit too young for that, so I might not be able to understand, but it's okay.
That's fine.
Okay, another lemma that we're gonna use. Okay, maybe I should not throw you a lemma like that without telling you why we're gonna use them, but I guess the first one is kind of like a basic sequence that everybody should know how it works.
Okay.
Okay, but here I'm gonna prove a lemma.
Okay.
Maybe I can do it in more general term, but well, I don't really care that much. I will just prove a version of it, but you can prove a more general version of it. So I will prove the following inequality.
So So I'm guessing all these lemmas are gonna be like something that we've all put together for the topic you're gonna discuss today.
Yeah. So basically, I need like some tool to be able to show that my sequence will be a Cauchy, but then we don't have much right now, so I need to get some tools.
Yeah.
So we have the following inequality for every natural number n, where n is bigger or equal to 1. Okay.
Okay.
And it will be a very elementary inequalities. We'll just say that 2n is bigger or equal to 2n.
Whenever I see 2 to the power of n, but it doesn't have a -1, I keep thinking of Mersenne prime.
And I mean, probably the easiest proof you can do is do it by induction. So, I mean, I guess we can do it for the case where n is equal to 1. So in the case n is equal to 1, we have 2 exposed on 1, and we have, which is just 2, and the other guys we have 2 times 1, which is also 2. Right? So maybe I can just write that. We have 2 exposed on 1 is equal to 2, and n 2 times 1 is 2. Does well, actually we even have equality in that case, but let's write it like that, okay, even though we have inequality.
Okay.
So when you do proof by induction, first of all, you show the base case, which is like the first natural number. In our case, we said that we care about n to be bigger or equal to 1, so we're gonna just do n is equal to 1 as the base case. And now we set the following inductive hypothesis. Inductive hypothesis. So there exists some natural number bigger than 1, just say that, such that the inequality hold. Okay. And now the goal is to do the inductive step, is to show the case n plus 1.
Okay.
So it's kind of like domino, right? All right. So for the case when n is equal to n plus 1, so we get that this guy. So we get on the left side, we get 2 exposed on n plus 1, but this guy we can rewrite as 2 times 2 exposed on n. Okay.
Yep.
And now what we're gonna do is we're gonna use the hypothesis, the inductive hypothesis on 2n. Okay. So pi. Okay, maybe I will just write on the top. By inductive. I'm writing like it is French. Inductive hypothesis.
Sorry.
We have that 2n is bigger or equal to 2 times n. So we're gonna apply this to this. So what we're gonna get is we're gonna get the following. So is that good so far?
I'm just writing everything down. So.
Okay.
Okay. 2 times n. Okay. Alright, so it basically says 2n is greater than or equal to 2 times n. Yeah, that's logic. That sounds like it logically makes sense.
Yeah. So basically, what we did, we just take this inequality and we multiply it from both sides by 2, which we know preserve the inequality. So that's why we get this. And now I'm going to do some algebra. So first of all, I want to write 2 times 2m as let's say I want to write it as 2n plus 2n. Okay.
Okay.
So here, nothing crazy I did. But what I will, so now I will use the fact that n has to be bigger or equal to 1.
Okay.
So I can I can have a lower bound for this guy. I can say it will be less or equal, therefore, to n plus 2. Because we said that n was bigger or equal to 1.
Okay.
Okay. And now here we can just factorize to 2, so we just get 2 times n plus 1. And then here we're done because we just showed that 2 exponent n plus 1 is less or equal to 2 times n plus 1, which is exactly the case n plus 1. Okay.
All right.
Therefore, we have the inequality we wanted. And as a corollary, so as a consequence of that, we are able to make we are able to prove that the following sequence is converging. Corollary 1 over 2n is converging to 0.
Okay.
And so we're gonna use this inequality. So let me show you how it's done. So what we're gonna do is basically we're gonna compare with the one that we previously showed.
Okay.
Yeah. So let's do the proof. I mean, there's a very more general way of. I mean, this sequence, there's like multiple variations that you can do which still work. For example, if you replace the 2 by 3, you should still get the. This is converging to 0, but for today we just need the 1 over 2n. Let epsilon be bigger than 0. Then what we're gonna do is what we want to do is we want to compare with an existing sequence that we know is going to 0. Okay.
Okay.
And here we'll use the fact that so we prove that 1 over n is converging to 0, right? But in the exercise I did for this week, you also have an exercise when you prove that if you multiply 2 sequences together, so if you multiply 2 converging sequences together, you still get a converging sequence. And one consequence of that is I can multiply a sequence by a number, and the sequence will still converge. So let epsilon be bigger than 0 by the previous lemma. Well, I guess I shouldn't say so. Okay, maybe I will not say the previous because it's like 2 lemma ago. But
yeah, there's 2 of them.
Yeah. So you
could probably say like by lemma 1 or lemma 2.
Yeah, I guess I should say that even though I didn't give their name, so I guess I did that. By lemma 1, we have that 1 over n is converging to 0. But by exercise, we also know by exercise, as an exo, we also have that 1 over 2n is converging to 0. Okay. And now we're going to use the inequality. So we know that this guy is converging to 0, so we can use this fact. So as 1 over 2n is converging to 0, therefore there exists some natural number n such that for all rank which come after that, 1 over 2n will be smaller than epsilon.
Okay.
Here again, I don't use the absolute value because I mean those quantities are always positive. And now I can use so maybe here I can assume that n is bigger than 1 because it doesn't really change much. So we just assume that n is bigger than 1 in the proof. Then I can apply the previous lemma. By lemma 2, maybe I will take first of all the n. Let n be bigger or equal to n. By previous lemma, so the previous lemma what it was saying, it was saying that 2 over n is always bigger or equal to 2n, right? But then now I can flip those. And what it do is I will reverse the inequality sign. I will get this, right?
Okay.
And now I'm very happy because now I have no. So this guy is also bounded by 0. Maybe we'll just write that. But on this guy is bounded by 1 over 2n, but this guy is smaller or equal to epsilon. Therefore, 1 over 2n is less than epsilon, which show that 1 over 2n is going to 0. Okay.
Okay.
Oh, here I'm sorry. This is supposed to be 2 times n. Yeah.
2 times n. Yeah, that's what I was thinking. I was like, which one is which?
So here we did something which we're going to be able to do in the real number, but right now in the rational we're very limited to that. So usually one strategy to show that a sequence is converging is compared to an existing one. So when we're going to deal with the real number, we're going to have a theorem called the squeeze theorem.
Okay, yeah, I'm familiar with that one.
Yeah, but right now over the rational it still hold. So yeah, I guess we could prove it for the rational number. Yeah, I guess that's the monotone theorem is false over the rational, but the squeeze is fine. So I guess we could have proved that, but that's beside the point.
So,
all right.
For all these lemmas, right?
Yeah.
And the proofs that we provided.
Yeah.
So what will be our next step from here? And like, what is the overall objective with these lemmas? Yeah.
Okay, so this lemma I will use it to prove the following. Okay.
Okay.
Which is a very well-known fact. So I'm gonna prove. So I will take an to be some kind of series. And I will take it.
So we're talking series now, no longer sequences.
Yeah, but series are just a special case of sequences. Like you just define your term as given by a series by a sum.
By a series, yeah.
Yeah, so it's just a special case. Okay. So we're gonna write this sequence, which is a series, right? And we're gonna show that it converge. So, what's this? It's 1 over. What is this? 1/2.
1 over 1/2. Like, what are you trying to show here?
So, I mean, those are supposed to be geometric series, but if I'm not misleading, this guy should converge to 1 over 1 minus the minus the how do you call the R in English?
Is it supposed to be like 1?
The ratio, right?
Oh, okay.
Yeah. It's just a specialized the case where it's a 1/2 because that's the care that we're gonna care for today.
So I'm guessing like basically because like you're trying to assume that basically 1 over 2n is similar to basically saying like a half to the nth power, right?
Yeah. Maybe I should write it like
a geometric series, right?
Yeah. Maybe we'll make It's a very special case of geometric series. Is the case where r is equal to 1/2.
Right.
And okay, for this time I will not show everything because there's one part that I want you to do it because it's a very classical thing to do it's a very classical proof by induction, which is very easy. So I mean, it's a good exercise. So we're gonna assume the following fact.
Okay.
Assume the following. So we're gonna assume the following. So okay, here I have to be a little bit careful. So I think I have to ask that. Is there constraint? I guess we could just assume it's okay, and it's bigger or equal to 1. I want you to show that the partial sum here I put, oh, here I'm supposed to put a key, I'm sorry.
Mm-hmm.
So the partial sum is equal to what? It's 1 minus 1/2. And if I remember correctly, this guy should be 1 minus, is it a half and half exponent n, I think? Let me double check. Oh, there's a +1, I'm sorry. Okay.
Okay.
So, I mean, you probably have seen that, I mean, in Euclidean calculus, when they show you that this sequence converges, they say, well, we're able to find the partial sum of this sequence, and we just need to take this guy to go to infinity. It's pretty much what we're gonna do. So, if we assume this fact, then our sequence becomes, so, using this fact, our sequence become an is equal to 1 minus n plus 1 over 1 minus 1/2, right?
This part says become, right?
Yeah.
Okay.
And maybe here I can just move a little bit stuff in our sequence, so I can remove the 1 by just taking the half out, like that. Okay.
Okay.
But now this is just an application of the fact that when you multiply to a convergent sequence, and when you add two multiplies when you add two convergent sequence, you still get a converging sequence. Because at the end, what is that? So first of all, the numerator is just the sum of two sequences.
Yeah.
One of them is 1/2. Well, I guess there is a constant there, and the other guy is just the constant sequence 1, right?
Yeah.
So those two sequences are converging. Therefore, the numerator is converging, and the denominator is just
it's just a
constant.
Number. Yeah. It's practically a number.
Yeah. Therefore, this sequence will converge, and the exercise we have in the sheet is that you can just take you can just look at where every sequence is going to. What's the limit of every sequence, and that will give you the limit of the sequence. So by exercise, we have that an is converging to 1 minus 1/2, because this guy is going to 0 by the previous.
Yeah, because it's like n power a half to the n power, but if you basically simplify it, it will be like 1n, which is 1, and basically 2n. And if you basically take n to infinity, basically 2 will just get bigger and bigger, thus closer to 0.
Yeah. But we already show like that formally, right? In the last already. But that's the intuitive idea.
Yeah.
Okay, therefore we're done. Okay. Now I was so mysterious, so now I can tell you why on earth did we prove all this?
Yeah, why is this all for?
Yeah, maybe I should start with sometime with motivation, otherwise maybe that's not so great. So what we're gonna do is we're gonna try. So okay, the goal of today, for the rest of the lesson, is to build a sequence of rational number Well, I will use the word converge, but it's not really the right one. To square root of 2. Okay. So here when I use the word converge, obviously it will not converge because square root of 2 is not a rational number.
Yeah.
But this sequence will be able to approximate as many terms as you want.
So I guess with all this, would this same technique be able to prove that, say, like pi you'll be able to, I guess, like make an approximation to, like, say, things like pi or other irrational numbers? with
Yeah,
this
you could
technique?
do that. You could do that, but I mean, right now it's kind of a bit complicated because we don't even know what pi is, right?
Okay, so this strategy is only for like this particular number in this case, right?
Yeah, I mean, yeah, there's some part of the proof that I'm gonna do that can be adapted to, for example, a similar case. For example, the square root of a square free number will be irrational, then you can do that. But yeah, I mean, it's kind of a niche proof, so.
Okay.
But it used like some very cool numerical analysis strategy. Okay.
Okay.
So it's going to be fun.
Okay.
So what I want to do is I want to consider the following function. So maybe I will write it as f. Okay, maybe I will try to give you like an overview of what we're gonna try to do. So we're gonna consider the following function from the rational to the rational.
Okay.
Which gonna just take x and send it to x squared minus 2. Okay. So zero of this function are exactly zeros of this function are equivalent to solve x squared is equal to 2, right? Okay. Okay, here I will use a lemma, but I think you saw it so many times in some book of proofs, so I'm gonna just not prove it because I think I mean, you can have as an exercise if you really want, but there is no rational solution to square to this equation here. Okay. In other words, that's the proof that square root of 2 is not cannot be written as a rational.
Yeah, I'm familiar with that.
Yeah. So we'll just take that for granted, and what we're gonna do is we're gonna build a Cauchy sequence.
Okay.
Actually, we're gonna build two Cauchy sequence because, well, the technique that we'll use, we kind of build you into a sequence. We're gonna build a Cauchy sequence an, okay, of rational number.
Okay.
Rational number. Such that f of an is converging to 0. Okay. And so the fact that okay, here we're gonna have to talk a little bit about continuity of the function f, but basically what's gonna happen is the sequence an will be Cauchy, so it's well behaved, and its image under the function, its limit will go to 0. So the way you have to interpret that is that an is approximating square root of 2 with arbitrary precision.
Okay.
And here the sequence an will fail to be convergent.
So is this like proof by contradiction?
Well, yeah, it will be basically a contradiction because basically if this sequence n is convergent, okay,
yeah,
because our function f is continuous. Okay, so maybe state this fact. As f is continuous, and I will explain what it means later. Well, actually, well, okay, I need a little bit more than continuous, but it's gonna be fine. If an is convergent, let's say it converges to a number a, right? Then f of an has to converge to f of a. But that will imply, so as we know that f of n is converging to 0, this will imply then f of a is equal to 0. Thus a would be a solution to xy is equal to 2. That would be a rational solution. Which cannot happen because the square root of 2, the root of 2 are not rational numbers.
Right.
So this will give us a contradiction. So what we want to do is to be able to build such a sequence AN. Okay. And now we're gonna use a technique in numerical analysis. Well, this is analysis, but it's used. I mean, you can basically write a program from that, which can compute you the with arbitrary precision the value of the square root of 2. Okay. And I will first of all do some drawing. Okay.
Okay.
So what we're gonna be interested is to look at the function f, which is, I recall, is given by x squared minus 2 on the interval 1, 2. Okay. Oh, this is supposed to be a minus 2, I'm sorry. Okay. So maybe I can just draw a little bit picture of what it will look like. So this function, if we look at this graph, will look something like that, right? So here we have the point 0, 2, and the graph will look something like that, right? And the point 1 will be here, and so this guy will be 1, and this guy will be 2. Okay. And basically, so basically, what we're gonna do is we're gonna use the fact that this function is increasing in this part.
Okay.
When we look at when we return ourselves to the interval 1, 2, and we're gonna use the fact that in some part of the function is negative and the other part is positive.
All right.
Okay. And okay, maybe I can here now draw you a little picture of what's going to happen.
All right.
I will try to write a big line because I need a lot of space for that. And I will move a little bit the square root of 2 because otherwise it's 2 in the middle and it's not. It's a bit hard to understand. So this is 1, this is 2. Okay. And let's say our square root of 2 is somewhere like there. Okay. It's not. I mean, usually it will be more in the middle, but if I write it in the middle, the algorithm will be a bit weird to look at. So I will kind of exaggerate and put it on the left. Okay. And so what we're going to do is we're going to build 2 sequences. So this method is called the dichotomy method, which means splicing the space in 2. Okay. So what we do is we start with some points. For us, we're gonna choose the boundary. Okay. So I have 2 sequences. Okay. And now what I'm gonna do is I'm gonna choose the point in the middle.
All right.
So the point in the middle will be somewhere like that, right? So x2 plus y2 over 2. That's the point in the middle of the interval. And what I want to do now is I want to look if the function is positive or negative on this guy.
Okay.
So we're gonna test that. So maybe I will write as an if. So if the function is positive, okay, then we set y1 to be equal to the point in the middle, and we let x1 to just be x0. Okay. If we get the opposite, so this is the case where the function is positive, then we do the inverse. We do the thing backward. So if we get the other case, then we do it backwards. So we set y1 to be equal to y0, and x1 to be equal to the average of the 2. Okay. And then in that, actually, we're gonna just do it by induction. So we're gonna just here I write it for 0, right?
Mm-hmm.
But here you can put n actually, and here you can put n plus 1. Okay.
Okay.
So what it does basically, so maybe I can just go back to the drawing. So the way you have to think of this is that this guy is supposed to be the 0, right?
Yeah.
And so everything which is on the right side of that will be positive, and everything which is on the left side is negative for the function, right?
Mm-hmm.
So what's gonna happen is, okay, maybe I can run a little bit the algorithm, at least on the picture, is that the point in the middle in the first iteration will be on the right side, right?
Right.
So therefore we're gonna have y1, which is gonna be this point, and x1 will just stay the other boundary, right?
Mm-hmm.
So what we have here is that we have now a new domain which is smaller. It's half the size of the first one, right?
Mm-hmm.
And now we're gonna repeat the same process. Okay, maybe I should not use red, maybe I should use blue. Okay, for the point in the middle. We're gonna choose the point in the middle. Okay, this doesn't look like the middle, but what on earth did I just write? Okay. Okay, we choose the point in the middle and we repeat the same step. Is it on the left or right side of the interval?
So with the point you drew in the middle, like restate the question.
So is it on the left side or right side of the red point?
Oh, the blue you just drew, right? It's on
the
right side. It's on the right side of the dot. Yeah.
Yeah. So what we're gonna do is we're gonna shrink our domain even smaller. So this guy would be y2 now. And now we can maybe repeat a couple times. So after that, we're gonna shrink, and now what you can have is that now it's on the left side, right?
Yeah.
So this guy, so as it's on the left, now we're gonna change the value of x. Now this guy is gonna be x3. Okay.
Mm-hmm.
And now we're gonna continue halving. So now it's gonna be on the right, so we're gonna get an interval like that. And well, right now it's kind of getting a little bit too cramped to be able to draw anymore. But you see the picture, I think, right?
Yeah, I see it.
Which is pretty cool, I think.
Mm-hmm.
So maybe I can show you actually so I wrote a little Python script that is basically just gonna do the thing I just told you, and we're gonna run it for a few iterations to see if it gives you a good approximation of square root of 2.
Okay, so how do you plan to show it to us?
So can I share screen on Discord and are you able to show it on stream?
Yes, just give me one quick second here.
Okay, now I just have to find where is my Python script.
Just do a pop-up screen for us. All right. Let me see if it. Yep, it's on my stream. Yeah, all you have to do is stream your screen, and then we'll show it for everybody. Yeah, I remember you were pretty excited to actually set this up.
I mean, that's a cool demo. You're gonna see it's a very basic script, but you will see the analysis required to show.
Yeah, just stream your screen for us. Okay. Yeah, I think we see it. Hopefully, you guys in chat can see it clearly.
So I'm gonna maybe just. I mean, you don't have to know a lot of programming. It's basically English, but we'll just maybe write through. So, so when I use the word def, it means a function. Okay.
Yeah.
And so the first function that I've defined here is just a function. It's just f of x is equal to x squared minus 2. Okay.
Yeah.
And this guy that I wrote as a solver, so it's so basically what it takes is it takes two initial value, which are our boundary of our initial domain.
Yeah.
So in our case, we want to take 1 and 2. And now we're just gonna, so the n is the number of iteration I want to do, because it's a computer, so I cannot run this forever, otherwise I would not get an answer. And so I basically just do a n loop of that.
Yeah. Yeah.
And then it's gonna run the following code. So first of all, it check if the point in the middle is positive. If that's the case, then it update the value of y.
Okay.
To be this point. Otherwise, it will change the value of x if the function f is negative on the middle. And now, so here I have some code which is gonna be basically called the solver, which is gonna give it the boundary 1 and 2, and we're gonna run for 100 iteration.
Okay.
Okay. And now we're gonna use the magic. So let me run the Python script. So Python main.py, and that's the answer you get. So as I said, we have two sequences, right? We have one like in the lower. We have like one in the lower we also have one in the positive side, right? We have x and y n. So those guys are the number we get after 100 iteration, which are very close to square root of 2. Yeah, I think they're like correct up to like I think all the digits we see on the left guys are correct. I think
it's probably like 100th of 100th of 100th of 100.
yeah. And if we run it even longer, then we will have even more
iterations.
Yeah.
Gotcha.
So now that I mean, we kind of run the problem and say it works. Now we have to show that actually the math checks out, and what the computer gave us was not nonsense. It was actually a real thing. Okay. Okay, now let's go back to the math.
Yep.
So as I said, okay, maybe here I will not prove. I will maybe not write the lemma and stuff like that. We'll just play with the sequence. So I will define the following sequence, as I said. So xn is gonna be so x1 is gonna be 1, and y1 is gonna be 2. And basically the thing I wrote on top, I can rewrite it at the bottom. So we are gonna have that. Well, basically I will just not rewrite the thing, but it's basically the thing that I wrote on top. Okay. That's the definition for a sequence. So maybe here I should change those for ends. Sorry if I'm a bit messy. I don't think I want to rewrite that, but it's okay. Okay, so as I drew in the picture, we need to show that f is increasing function. Okay. Okay, how do I want to show that? Oh, well, I guess I just have to show that x squared is an increasing function on the interval 1 to 2, right? Okay, I guess I'm going to do that. Well, actually, I'm going to show that, okay, first step. Show that f is increasing. Also, I have a quick question for you.
Yeah.
So here, when you look at my definition of my sequence, right? I have two cases, right? But as you see, there's the first case where the function takes strictly positive value, and the other case where it takes strictly negative value. So you might say I'm missing a case, right?
Yeah.
When the function is equal to 0, but
zero.
Why is that not an issue for me right now?
Because the point you're getting closer and closer to is technically 0 in this case. I mean, like, not literally 0, but it's basically you're zeroing in on the actual value you want to get to, but you're trying not to get on the point. You're trying to get very, very close to it.
Yeah, but I mean, for example, in the algorithm, we can imagine that at some point I reach when I take the middle point, I get 0, right, in the function.
Yeah.
If that was the case, the Python script that I show you would crash. Because I don't do this case. There's no the script doesn't know what to do in that case. It would crash, but it didn't.
Yeah.
Why is that?
Well, if it did go to 0, you said it would crash, right? So.
Yeah.
I'm guessing because since you didn't make it equal to 0, it wouldn't have to do it like an infinite amount of times. This particular setup.
So what we did is we started with the rational number, right? 1 and 2.
Yeah.
And the point in the middle is given also by a rational number, right?
Yeah.
We just basically take the average of two rational numbers to the rational number. But what it would mean if f of a rational number would be equal to 0?
What would it mean if the rational number was equal to 0? Is that what you're
saying?
Well,
what does it mean if the function at some point is equal to 0? What it means, concretely?
I mean, it would probably mean that xn plus yn would have to equal 0 at that point.
Well, not really, right? Because if the thing I put inside the function is equal to 0, the function is going to get the value -2. Well, okay, maybe my question is not so clear, but basically, as we're feeding rational number to the function f, if the function f at some point reached the value 0, when we feed the rational number, we get that's not possible, because otherwise we would have a rational solution to the equation x squared is equal to 2, which cannot happen because we show that square root of 2 is not a rational number, so we don't have to. So this is not possible.
Oh, it's basically you're trying to prove a contradiction which is non-existent. That's why the program would crash.
Yeah. So basically, if our sequence of rational number at some point would give us 0 when we evaluate to the function, then it would mean that we have a rational number which is a solution to x squared is equal to 2, which cannot happen. That's why I don't have a third case here, is because the third case is just not possible because of the fact that square root of 2 is not a rational number.
Okay.
If I was, for example, instead I was solving the equation f of x is equal to x squared minus 4, then the case where f of x is equal to 0 would be something that I should have to care about. Because they're a rational number which obviously satisfy this equation, namely x is equal to 2.
Yeah.
But I don't have here to do that here. Okay, so the first step is to show that f is increasing, and what we're going to do is we're going to prove that the function g of x, which is given by x squared, is increasing. Is increasing for positive x.
Okay.
So maybe I can give you a little hint about. Maybe I'll show you how it works. So.
Okay.
Let's assume that x and y be a positive number. And we can assume that one is bigger than the other. I guess assume that x is bigger than y. And what we want to show, the goal, is to show that g of x is bigger or equal to g of y.
Okay.
Is smaller or equal to g of y, I'm sorry.
Okay.
And what we're going to do is we're just going to play with the algebra.
Alright.
Actually, I might want them to be strictly increasing. So maybe I will assume that x and y are different.
Okay.
And I want this bound to be stricter. Okay?
Okay.
So the fact that y is bigger than x means that y can be written as x plus some r, right? Where r is some positive quantity, but as we ask for strict inequality, we're gonna have a strict r, a strict quantity, which is yeah. And now let's just play with the algebra. So let's evaluate g of y. So g of y is, well, first of all, it's g of x plus r.
Mm-hmm.
But g itself is just squaring the thing, right?
Yeah.
So we're gonna end up with something like that. And now we can just expand this product. So we're gonna take x squared plus 2r times x plus r squared, right?
Mm-hmm.
And what we can say about that is that r and x are positive, right?
Yeah.
So maybe here I have to be a little bit careful. No, okay, I can just okay. Okay, first of all, as those guys are positive, I can just remove this guy.
Mm-hmm.
So we have a bound. Okay.
Yeah, so you said basically, like, going back, like, you said you took out the 2 times rx because if it's positive, it's no longer needed in there, right?
Yeah. I mean, it adds some stuff, but it gave a positive contribution. That's all it matters.
Like, is it safe to, like, kind of, like, think of it as, like, you know, the constant after an integral? Like, it's there, but it's not really, like, important?
Well, here he changed the value of the numbers, but
yeah.
I mean, if I just care about having inequality, I can get rid of it.
Okay. All right.
Okay.
Uh-huh.
And now what I get is I get a strict inequality with x squared.
Okay.
Because as r is strictly positive, r squared is also strictly positive. Yeah.
Mm-hmm.
But then what we have, so maybe I can just rewrite the thing. So what we have here is that we have that. So x squared is less or equal to g of y, right?
Mm-hmm.
If we just like rewrite the thing, but x squared is exactly g of x, right?
Mm-hmm.
By definition, thus I've shown that g of x is strictly smaller than g of y. Thus g is strictly increasing.
Okay, strictly increasing. So the reason why you took out the 2 xr and the r squared is basically because since it's already like positive, it's still making x squared like increase, basically, right?
Yeah, so what I knew is that g of y is bigger or equal to x squared plus r squared, right?
Uh-huh.
But I know that r squared is strictly positive.
Yeah.
So if I get rid of them, then I know that x squared has to be strictly smaller than g of y, because r squared has a positive contribution to that. So if I get rid of it, I'm certainly losing stuff, right?
So how did, like, was there a condition that you basically reduced the parameter from like greater than to equal to just greater than?
Yeah, and here justified by the fact that r squared was strictly positive.
Oh, okay. So I'm guessing the what it's supposed to say is that gy, which is g x plus r, is supposed to be on the left side of like the greater than.
Yeah.
Okay.
Yeah. So basically, I summarize here the inequality that we play with. We have that x squared is strictly smaller than g of y.
Okay.
But then x squared is just g of x, so therefore we have this.
Oh, okay.
And
that's
as
that's pretty interesting, like to show that it's increasing.
Yeah, it's kind of fun. And as a corollary of that is that we have that f is also increasing. Because f of x is just equal to g of x minus 2, right? And the minus 2 doesn't really change the I mean, I think a constant doesn't change the fact that the function is increasing or not. So f is also increasing.
Okay.
All right. What I need next? Okay, now that's the important part. I want to show that now that xn and yn are Cauchy. Okay.
Okay.
So for doing that, first of all I will find a bound. Okay.
All right.
So the bound I'm gonna use is the following. So yeah, this one is not straightforward. I need to do a few preparations before that. So I will show for all n.
Okay.
We have xn plus 1 minus xn is less or equal to xn minus yn over 2. And the same goes for y.
So the first one basically says xn plus 1 minus xn, right?
Yeah.
Okay.
All right.
Mm-hmm.
So we're gonna prove them. I'm just gonna show one of them because I mean the proof is the same for the two. So there are two cases, right? So maybe I will just show one here.
Okay.
Because I mean, other than that, they're basically the same sequence. I mean, not exactly, but they're very similar. So the argument will work for the both of them.
Mm-hmm.
So for one, so there's two cases. So as our sequence depend on the fact that f of xn plus yn plus yn over 2 is have some sign, right?
Yeah.
So that there's two cases to consider.
Mm-hmm.
So let's do the case where this guy is positive, okay?
Yep.
In that case, we have that xn plus 1 is equal to xn, right?
Mm-hmm.
Therefore, xn plus 1 minus xn is equal to 0, which is definitely less or equal to xn minus yn over 2, right?
Mm-hmm.
Because it's literally 0, so there's nothing to prove.
Yeah.
And for the other case, second case, is the interesting one, is that we have that the function of x of n plus yn over 2 takes strictly negative numbers.
Mm-hmm.
And in that case, we know that x of n, if that's the case, we know that x of n plus 1 is going to be the half of those guys, right?
Uh-huh.
And now let's have a look at the quantity. So we have xn plus 1 minus xn. And now we're just going to play a little bit with it.
Mm-hmm.
So first of all, we're going to expand what is xn plus 1. It's xn plus yn over 2. And minus xn, I'm going to just put it on 2 as well. So we're going to end up with minus 2 xn, right?
All right.
But now if I simplify the algebra, so I have the xn that I can simplify, I will end up with xn minus yn is equal to 2, right?
Uh-huh.
Therefore, xn plus 1 minus xn is less or equal to xn minus yn. Okay.
Okay.
So this was some useful bound. So I know the difference between the two successors in the sequence are bounded by this quantity, right?
All right.
Okay. So what now I'm gonna try to do is try to have a better understanding of what's the difference between xn and minus yn. Okay.
Okay.
And maybe we can. Okay. Actually, here we can see the answer really easily. So if we go back to the drawing I did a while ago. Here. So what was I doing is I was taking half of the interval at each time, right?
Yeah.
And then slicing it in two, right?
Yeah.
So basically the xn and yn are the boundary of the interval, right? So at x1 y1 I have the big interval. After that I get this interval. And the further I go, I get a smaller and smaller interval.
Yeah.
And so as we're choosing the point in the middle at each time,
yeah,
what's gonna happen is that the interval is gonna get half at every step, right?
Yeah.
So basically the length of the interval is gonna be 1/2n. Because we're halving at every step. So xn minus yn, which is our xn and yn are the two bounds, they will have to be equal to 1/2n. And that's the thing we want to show now. Okay. So okay, let's do that. Okay, maybe okay. Well, actually, it's a very similar proof, so maybe I will just okay, by the same. It's actually playing with the same arguments that we just stated. By the same argument, we also have so what is it? It's x plus 1 minus yn. Oops. Plus 1 minus yn plus 1.
So this corollary you wrote is basically just to say that the amount of times that we are, I guess, bringing x and y closer and closer is supposed to be less than the amount of times that we cut it in half previously.
So yeah, so basically the way you have to think about it is that xn minus yn is the previous size of the interval, right?
Yeah.
And the guy on the left is the size of the interval for the next iteration.
When we shrink it more because it's plus n.
Yeah. And as we said, we're halving the interval at every time, so it's quite natural that the size will get divided by 2.
So what you wrote just now in red, by some, is that supposed to be interval or what is that?
Okay, maybe here I didn't finish my sentence. By some similar argument.
Oh, similar argument. Okay.
You basically just play with. I mean, it's the same thing. It's just you have equality. I mean, it's basically like the second case. You have that. So
now you're writing x n plus 1 y plus n plus 1 is now equal to x n minus yn 2.
Yeah.
So now you're setting them to equal each other?
Yeah, now they're equal.
Okay.
Because previously I was comparing xn plus 1 with xn, right?
Yeah.
And those might not be equal because sometimes xn plus 1 would be equal to xn, so it's going to be 0. But if I look at the difference between xn plus 1 and yn, then this quantity will always be given by the thing on the right because I'm halving the interval at every step.
Okay.
And the argument is pretty much like this guy. You just follow this guy and you will have the same. You will have the proof of the thing I wrote in red.
Okay.
All right. So far, so good.
Oh, actually,
And-
before we get to that,
Yeah.
the one that you wrote the red arrow to, let's see, xn plus yn minus 2 xn, right? Is
Yeah.
that xn? So where did the two xn came from again?
It came from this guy.
From the xn, right?
Yeah, because I put it on 2, right?
Uh-huh.
So I had to put a 2 at the numerator as well.
So I'm guessing that xn plus 1, that is supposed to be equivalent to the
So this is
x.
that. Let's go. Yeah.
Mm-hmm. Okay. Like I guess like so xn is equal to 2 minus 2 xn.
Yeah.
I'm trying to remember where we got that from.
So it's just the fact that xn plus 1 is equal to xn plus yn over 2, right?
Yeah, that part I get.
But then I have a 2 in the denominator. If I want to subtract them, I have to put them on the same numerator.
Okay. Like, yeah, I forgot about that. So basically, it's just multiple. Like, I forgot
Yeah.
that we're doing it from. I forgot this, and I was thinking like, wait, oh, this is similar to basically saying, minus. Yeah, I didn't see this part.
Yeah.
So I wasn't thinking of this.
Yeah.
So that's what I was thinking about. Okay. I'm okay. Now it makes sense. Okay.
Okay.
Yeah.
Okay.
Mm-hmm.
So now we have this, which tell you the distance between 2 for like the next step, right?
Yeah.
And we know what's the difference at the start, right? Because we know that x2 is equal to 1 and y0 is equal to 2, right?
Mm-hmm.
Therefore, the difference between x0 and y0 is going to be 1.
Yeah.
And if we use this formula by induction,
Mm-hmm.
so what we're going to find is that, so maybe here I will skip the proof because it's a proof by induction and it's not very hard. What we're going to see is that the distance between xn and yn is equal to 1 over 2n.
Okay.
And this proof, I mean, this is just a proof by induction, is very straightforward because you use those two facts together.
Okay.
Okay.
Mm-hmm.
Okay, I will skip the proof because it's not very hard. Okay. And now we're ready to show its Cauchy.
Okay.
So okay, here maybe I will just write down the ingredient that we needed. So
Mm-hmm.
to show its Cauchy, we will use so we will use the fact that we have the following bound on xn plus 1.
Mm-hmm.
So we know this guy is less or equal to xn minus y and over 2, right?
Mm-hmm.
And we're gonna use this bound as well.
Okay.
And so previously I showed you that we proved the geometric series for the case r is equal to 1/2, right?
Mm-hmm.
This will play a role right now.
Oh, okay.
So, okay, here's the deal.
All right.
So, okay, I'm gonna do the proof. So I will use let epsilon be greater or equal to 0. So first of all, I'm gonna do something which is a little bit counterintuitive, but you will see later why I do it.
Okay.
So it's kind of a trick in the book that you have to learn.
Okay.
Like you have to see it once to understand it, but it's a very useful trick.
All right.
So I'm gonna use the fact. So okay, here I have to be a little bit careful though. I think I'm fine with this series. I might have to put the factor out. I might have a factor out, but this should work. So I will use the fact that we know that the geometric series converge.
Okay.
Okay, so we know that the sequence an given by 1 over 2n is converging.
Okay.
I mean, we even did stronger. We've even like found the this series is converging, but I don't really care about the value actually.
Okay.
I will use just the fact it's converging. Okay.
Okay.
And one thing that we showed earlier, I mean, in earlier course, was that when you have a convergence sequence, it's automatically Cauchy. Therefore, an is Cauchy. Okay.
Mm-hmm.
And what's gonna happen is that therefore I can write the coordination to be Cauchy, so it means gonna exist some rank such that for all p and q which are of greater rank,
Okay.
I would have that a minus aq is less than epsilon, right?
Mm-hmm.
But if we use it on this series, look what's gonna happen. So maybe I can just write AP and AQ. So AP is just gonna be this sum.
Mm-hmm.
And AQ is gonna be this guy. Okay.
Okay.
So if I subscribe the two, if I sub the two together, so here I can suppose a little bit more. I can suppose that, for example, P is bigger or equal to Q, because either one of them has to have that, right?
Okay.
So I will just assume it's P. I mean,
P is bigger than Q,
yeah.
or equal to whichever.
Yeah. Therefore, using those guys, what I get is I get that AP minus AQ is actually, well, here maybe I should write the actual sum instead of writing that. So it's 1 over 2 exposant k is actually the sum from k is equal to q to p of 1 over 2k. Okay.
Okay.
So I mean, so are you used to a summation like that?
Well, the indexes are the same for K, so
Yeah.
The only difference is that P and Q, but since P is bigger, then basically, yeah. So basically, it's like you're just adding P to Q in this case, but Q is still within P in this case.
Yeah,
So
and
it works. Yeah, it works.
Yeah, here I was a bit sloppy. I think I'm supposed to add the Q plus 1, I think.
Yeah, my thought is basically Q is in P, so we don't need to write like, P plus Q or something like that, because Q is already in, like, where the summation symbol is P. Yeah, okay.
It should be something like that.
Did you write Q plus 1?
I think it's Q plus 1. Okay, so what's going on? So we said that Q was smaller.
Yeah, Q is smaller or equal to P.
So it will reach the rank Q, right? So as we're subtracting together, we're gonna get rid of the terms where K is equal to Q. So it's supposed to start like Q plus 1.
Okay.
Yeah.
Okay.
And I guess if P is equal to Q, then this guy is just 0.
Okay.
Yeah, it makes sense because I mean, we can subtract the same quantity, so this guy would be 0.
Yeah, I'm guessing like it's kind of an interesting thought where it's like K is basically like, oh, we know we have Q terms in there, but we also have one more summation symbol from P, but Q is technically in P, so plus 1, yeah, it makes kind of sense when you think about the summation symbols.
Yeah. And now we're gonna use the trick. So the famous trick that we're gonna use is so we know that xn plus 1 minus xn is bigger or equal to what is it? Xn minus yn over 2, right?
Yeah.
But we know this guy what it is. We know that xn minus yn is the side of the interval, and we know he's getting half at every step, so we're gonna end up with 1 over 2n plus 1.
Yeah.
Yeah, and here I will just check to sure I'm not screwing up. I think it's right. Okay. Okay, so here it's a bit annoying, but I have to change it.
Change which part?
The sequence I chose. I'm supposed to take 1 over 2n plus 1.
Okay.
And yeah, there's a bit of in this that I have to have that. I'm sorry. That was the thing I was scared at the beginning, but I guess my scare was justified.
Oh, okay.
Okay. Okay, we're really close now.
All right.
Okay, so here I might have also to add a little plus 1 at some point, but let's forget about that. So let P and Q be bigger than big N. Okay.
Okay.
The same big N that we use for the Cauchy.
Yeah.
The phi series is Cauchy, and we're gonna show that xp minus xq is actually Cauchy. So we want to show. Not our goal.
Okay.
Is to show that xp minus xq is less or equal to epsilon.
All right.
Yes, if we're able to do that, then we're done. We've shown that xn is a Cauchy sequence.
Okay.
And now we're gonna do some very dirty trick.
All right.
So, first of all, we're gonna assume that p is bigger than or equal to q.
Okay.
Or is that the thing I assume above?
Yes.
Yeah. Okay,
Yeah.
okay.
P is greater than or equal to Q. Yeah.
Okay. And I will actually assume that this is strictly inequality, right? Because if I have p is equal to q, then obviously xp is equal to xq. Therefore, the difference is 0. So
yeah,
there's nothing to show. So I would assume that, and what it will allow me to do is that I will be able to write p as q plus some quantity. Let's call it m.
Okay.
Where m is just positive. Okay.
Okay.
Okay. And now we're gonna have fun. So what I'm gonna do is so now xp can be written as xq plus m.
Q plus m. Yeah.
Yeah. And now we're gonna use a famous trick. I mean, I think you did it in calculus 1 or 2, maybe 2 actually. Well, at least when I was learning calculus, I think we did that in calculus 2. We're gonna write the following sum. Xk plus 1. Here I have to be a little bit careful. I think it's supposed to be plus m. Oh no, it's supposed to be plus q, I'm sorry. Minus k plus q. And I think now everything checks out. Okay. Okay, have you ever seen this trick in your life?
I think I may have seen it like on YouTube, but I barely remember it though.
So the idea is that if you have a sequence,
okay,
maybe I can write it.
This is like a side note, right?
Yeah. So this guy is a side note. Yeah, here I'm getting messy because the proof is very long. So
yeah.
Okay. So let's say you have a sequence, and then you consider this following sum. Okay. Where the degrees shift by 1.
Yeah.
Okay. So what's gonna happen is basically so the first term cannot, so the a when k is equal to 0, this guy can never be cancelled by the other guy.
Yeah.
Because this guy starts 1 degree higher, right? But all the other terms, those will be cancelled by this guy.
Yeah.
Because you're gonna have the plus and the minus the same sum. And so pretty much everything will cancel out, except the first value here, and also the last value on this guy.
Okay.
because it's one step higher. So what we're gonna end up having is this is AM minus A0.
Okay.
And that's pretty much what I did here.
So basically, let's see, you wrote xk plus 1 plus q is minus xk plus q. Yeah, the only difference is it's just one.
Yeah.
Oh, so basically because there's m there, basically the m minus 1 will basically get rid of that 1 that's in.
Yeah,
x.
exactly. Yeah.
Okay. I see that.
That's
Yeah,
the idea.
yeah. I knew it was some. I knew the trick had something to do with the summation symbols. I'm like, wait, where do we go from there? Because I think I seen this in when I was watching a lecture on differential equations, because they were doing reviews on series and sequences.
Yeah. So in French, I think what's the name we use to call them? In French, we call it telescopic sum.
It probably might be the same thing.
Yeah.
In English.
Yeah. So that's a very well-known trick. And
okay.
and now the reason is why on earth are we doing that?
It's just to reduce our workload.
Yeah. So. Because basically we just take something which is very simple and then we make it very complicated, right?
Yeah, but it makes the math easier.
So why are we doing that? Is because we're gonna apply the triangle inequality.
Okay.
So this is a more general form of the triangle inequality. You can do it for arbitrary sum.
Yeah, I've never seen it with series and sequences, actually.
Well, it just worked for partial sum, but okay, here I really have to not make a mistake. Okay, we get that.
Okay.
So this is just the triangle inequality. Maybe I will write on the right. And now this guy is kind of cool, right?
Yeah.
Because if you look at it, it's the difference between two terms.
Yeah.
So this guy. So the thing in the absolute value we actually have a bound for this guy. Actually, where is the equality I need? Okay, maybe I'm completely off with the thing I said before, but we're gonna use this guy.
Okay.
So I guess those would be. Or maybe I did not get the good inequality on the Cauchy sequence. Maybe I would have to rework some stuff. But okay, we're getting close. Okay, so if I use the thing on the red on this guy, I will end up with this guy is bounded by 1 over. Is this n plus 1? Okay, so this guy is bounded by q plus k plus 1. Is that right?
Let's see, because it's supposed to be. It's like 2n. Yeah, because this is supposed to be plus. That seems right.
Okay, we're gonna hope it's right. Okay, now I can rewrite the sum first.
Yeah.
I don't want it to start at 0 anymore. I will want it to start at q. So now it will go from q is equal to k is equal to q. Yeah, this is always dangerous to do reindexing on the fly, but
Yeah.
And okay, well, where is this sum finish? So we have n minus 1. So oh crap! Did I do it wrong?
Did you originally wanted you wanted k to be to equal 0, right? Yeah. because this one has like k equal to q.
Yeah. I guess I can. Yeah. Okay. Okay. Maybe I can write 1 over the thing I want. So I would have. So what's the first value of this guy? K is equal to 0. It's going to be q plus 1. And the most value on the top will be q plus m, right?
Mm-hmm.
Yeah, because the -1 and the 1 cancel.
Yeah.
Okay. Oh, actually, okay, my bound is maybe not that bad. Let's see. Oh, okay, I see. Okay. Okay, so what was q plus m? It was p. So this guy can be changed to p. All right. Okay, so maybe now we have sort of a mess. So we'll just restate what we have now. So we have shown that xp minus xq is bounded by p k is equal to q of 1 over 2k plus 1. All right.
Okay.
And now let's go back to the Cauchy we had before. So I will go back here, okay?
Where?
Well, I think you can click on my name on the. Okay, you see me. Okay, did I choose the? Okay, I think my initial sequence was good.
Okay.
So now I have to remove the 1. Sorry about that. Oh yeah, okay, that's the thing, okay. Okay, I can either have this sequence starting at q plus 1, right?
Uh-huh.
But then I will have the wrong bound. Hold up.
Mm-hmm.
I mean, we're very close at this point. Alright, I might have to choose P and Q to be bigger than n plus 1 instead to have the right matching indices. I mean, it doesn't really change much, but okay. The point is that this series right there,
Yeah.
I mean, this sum you have here is the partials is the you can apply the Cauchy criterion on the sum of that, right?
Uh-huh.
And what you should get is this guy is bounded by epsilon.
Okay.
So that's what you want to do, but now I have mismatched indices, which make me a bit, which make me in trouble. So let's see if we can change those on the fly.
Okay.
Yeah. So what's that? Where did I do wrong here? Okay. I think I have a easy solution.
Okay.
Okay, sorry, it's just become very messy. So what I can do is I can actually put the 2k plus 1 here.
Okay.
But now I will have to change the bound above for p minus 1. K is equal to q. But now I have 1 over 2k plus 1. Okay, so this guy we know it's less than epsilon, right?
Okay.
For every choice of p and q which are bigger than n, right?
Right.
And okay, if I have that, then I'm done. Because at the bottom, I almost have that, but I have a p, right?
Mm-hmm.
Instead of a p minus 1, but at the end, p will still be bigger than n, right?
Mm-hmm.
So it's kind of confusing. Maybe I should call this guy p0 instead.
Okay.
Yeah, I mean, it's kind of better the way I write, but okay. The point is, okay, if this bound hold, right, for p minus 1, so it's all for every p and q which are bigger than n, right?
Mm-hmm.
So in particular, I can replace p by p plus 1, right?
Yeah.
Because it will still satisfy. Therefore, I have the bound where p is on the top and k is at the bottom. And we have 1 over 2k plus 1 is less than epsilon. Okay, that's the bound I need. Sorry if it's getting messy.
I'm sorry.
Yeah. I did not plan the end of the. I didn't plan really the proof, so we're kind of getting what we get. So the fact that this is less than epsilon just follows from the thing I just put on blue on the top.
Mm-hmm.
Sorry for the mess.
Sorry.
And this show that x is actually Cauchy.
Okay.
Because p and q were chosen to be arbitrary number which are bigger than big N, right?
Mm-hmm.
So this show that the xn is Cauchy. Okay.
Mm-hmm.
So maybe that's a trick like sometimes you have to use in analysis doing this thing. So maybe I can just recap the argument because now it's kind of getting messy.
Yeah.
So the initial plan was to so really where the big idea come from is from there.
Uh-huh.
Okay. Take this thing that looks simple and then use a telescopic sum to make some sum up here. Okay.
Okay.
And the idea is that we know what is the difference between two consecutive terms, right?
Yeah.
Because we calculate them earlier.
Mm-hmm.
And so what you do is then I mean we didn't calculate, we just had a bound on it. And the difference here, so we have a bound here, and it was 1 over 2 k plus 1, which is some kind of series sum, right?
Mm-hmm.
But the sum that we get here, we know it converge.
Yeah.
The series converge.
Mm-hmm.
Therefore, by the Cauchy criterion, it means that if you start late on your sum, at some point this quantity will be less than epsilon.
Uh-huh.
That's kind of the whole idea, and that's why we're able to get the bound that we have at the bottom.
So basically, you use the triangle inequality to basically reduce it to, I guess like the thing you marked in blue, which is like.
Yeah.
Okay.
Yeah. I use the triangle inequality to have this to obtain that my quantity I carry is bound by this.
Yeah, because the first part, the one you marked in red, right?
Yeah.
That's supposed to define. Let me see. Yeah, it's a lot. Where did we start it with? Okay, yeah, epsilon. So this part would be the proof, right?
Yeah.
Okay. That way we'll know where it starts. So let epsilon. Yeah. So we have the sequence, or is this a sequence or a series?
It's a series.
It's a series, right? It's a series, right? Because it has the summation symbol. Okay.
Yeah.
It's converging, and then we basically have to show it's Cauchy by basically doing this.
No, we don't have to show it's Cauchy. We use the fact it's Cauchy.
Oh, what I meant is that we use the definition of what.
Oh yeah.
Define Cauchy, like basically to show. Actually, to show it's Cauchy, we use the definition of what it means to be Cauchy. That's what. I was trying to say.
Yeah.
Okay, so. So the one in white, do we ignore that one that you wrote, and we just take the one that's in blue? Or
yeah, so we use all of them.
Oh, we use all of them. Oh, okay, so it's all part of it.
Okay, so if you use the strict definition, we just get this guy, right? but then if we do this, if we change the indices,
Okay.
for we replace k by k plus 1, then we get the one in the white, right?
Yeah.
But then this equality holds for every p and q which are bigger than n.
Yeah.
In particular, it works if I replace p by p plus 1. And the case where I chose p is equal to p plus 1 is the one on blue.
Okay, so so is the blue one just the better?
Yeah, that's the one. That's the final product that we're gonna use at the end. Yeah.
So technically, the one in blue can also be the one that's like the summation symbol with p and q equals p plus 1, right? So this is just so the blue one is just a better approximation of this one, right?
Yeah, sort of. I mean, the reason why blue is better is because the bound that I get at the end.
It makes it simple. It makes it much more.
Yeah.
Follow. Yeah. Both are correct, but like this one is just a little bit better compact. Yeah. I get what you mean. That's what I was asking, because it's like it's not like they're two different. It's not like it's not like this the white one in white is like gonna lead to the one in blue. It's just one is just better than the other. That's basically what it is. So you can use either one of them.
Yeah, it's just because at the end I get the one in blue which show up in my.
Yeah, I mean doing summation symbols is a bit of a trouble. Yeah, so I get what you mean.
Usually, I mean, if I did like a scratch proof, I would probably have started at this step.
Let me see which step you mean.
At this step.
Yeah, I know we had to
find
do
the
this.
Bound. Yeah, and then use the fact that my sequence is Cauchy to. And now I will have magically find all the correct indices, but I didn't, so we get into a mess.
No, I think that's how it is with proof writing mainly. You just have to like do it, and then you realize something's off, and then you're like, what did I do wrong? And then you go back and you're like, oh wait, I could have done this.
Yeah.
Okay. Well, that was a lot though. That was a lot.
Yeah.
So how much further do we did we already complete the proof? Or
so right now we show that xn and yn are Cauchy.
Are Cauchy, right?
Yeah.
Okay.
Xn and yn are Cauchy. And now what I would like to show is that f of xn is converging to 0, and y of fn is converging to 0 as well.
Okay.
So basically, what this will tell us, so the fact that the sequence is Cauchy here, will basically, so as I mentioned before, a Cauchy sequence are supposed to be sequences that converge, right?
Yeah.
But they just don't converge because, I mean, maybe the space is missing point, which is exactly what's happening over the rational number.
Okay.
And the function f is kind of a nice function. It's a continuous function, so we can interchange the limit and the sequence together.
Yeah.
And what we would like is that this sequence is not like any rubbish sequence. It's actually a sequence when you apply f, you get a thing that converges towards 0.
Okay.
That's kind of the thing that you want to show.
Okay.
So maybe I can guide us a little bit. Okay, so here it's a bit annoying. So first of all, I will show that f of xn is Cauchy.
Okay.
Okay. And I'm gonna use a very specific fact, okay?
Okay.
Which is useful. Is that the function f, which is given by x squared minus 2.
Okay.
So, okay, here I have to be a little bit careful because usually if you have a continuous function, the convergent sequence are mapped to convergent sequence, okay? But my problem is that my xn and yn are Cauchy sequence.
Okay.
And there is actually counterexample of continuous function mapping a Cauchy sequence to something which is not converging.
Okay.
So I need a condition which is stronger than continuity. And we haven't talked really about continuity, so I will just introduce this once, and Later, when we do more analysis, I will talk about it more properly, but for today is going to be fine.
Okay.
So what I'm going to do is I'm going to look at the function f defined on the interval 1 to 2. Because I mean that's really the point, the part that we care, right? Because we basically only use this part.
All right.
And okay, what's next? So I will play a little bit, okay, with it. So let x and y be inside of this interval, interval 1. Sorry, x and y be inside of the interval 1, 2. Then I'm gonna write f of x minus f of y.
Okay.
Okay. Now I'm just gonna restate the definition. So this will be x squared minus y squared.
Okay.
Okay. The two cancel out because checking from the same side. But then now, so now if I use a little bit of algebra, the thing on the right is the difference of 2 squared, right?
Yeah.
So it's factored out as x plus y times x minus y. And now I can just use the fact that the absolute value is homogeneous, therefore I can write as the product of the absolute value. Okay.
Okay.
But as x and y are inside of the interval 1, 2, right? The quantity x plus y is bounded, right?
Yeah.
The worst case scenario is that x and y are both equal to 2, right?
Yeah.
So this guy is bounded by 4 times x minus y. Therefore, we have f of x minus f of y is less than 4 times x minus y. Okay?
Okay.
And this is a stronger condition than a continuity. So usually when you have a function which satisfies this one, so you're able to find some constant time the distance between your point is smaller or equal to the value of your function, like that. We call such a function Lipschitz.
Lipschitz?
Yeah.
Okay.
The Lipschitz function.
Where did the 4 came from? Within the less than or equal to 4 x minus y. Where did the 4
it comes from the x plus y. So as we restrain ourselves to x and y.
So if it's if x is equal to the square root of 2 and y is equal to the square root of 2, does that basically if it's squared then basically it becomes 2 plus 2? Is that where you got the 4?
No, it's even simpler than that. So x and y are inside of the interval 1, 2, right?
Okay.
So the worst possible, the biggest possible value that you can have from two numbers inside of the interval 1, 2 when you add them together is that the 2 will be equal to 2, right? That makes sense. So x is equal to 2 and y is equal to 2, right?
Yeah.
So that means that this sum, x plus y, at the very most, it has to be less or equal to 4.
Okay.
Because if you take any other choice of x, then you get something which is smaller, right?
Yeah.
So this is a bound.
Okay.
And this is called a Lipschitz function, which are continuous function, but I don't want to go to that, and they're a bit stronger here.
Okay.
Under those hypotheses, now xn has to be f of xn has to be Cauchy. Maybe I will just write it down. F of xn is Cauchy. And let's do the proof a little bit quick, because we're kind of running low on time. So let epsilon be greater or equal to 0.
Oh, hold on. I think we're facing another problem with the Excel draw again, because I only see part of what you wrote.
Oh no! So I will refresh my page and then I will be missing parts. Is that it?
Yeah.
Or maybe today is a good day and it's gonna work. I don't know. Oh, okay, I see part of it. Oh no, never mind. Wait, are you?
Yeah, I don't see your cursor anymore.
Yeah, I don't see you neither in the room, so I guess. Oh.
Do you want me to share the link again?
Yeah.
Just go in here.
Okay, I see you now, I think. Oh yeah, I see you.
Yeah.
Okay, show me where we are because I don't see the text I wrote.
Let's go down here. I'm just going to erase what didn't show up. So.
All right, that's fine.
Yeah. Oh dang, this proof is so long. Okay, I'll just erase what wasn't completed. So I'll just draw a line where you can write. So underneath this line.
Okay, it's fine. Okay, so we'll show that f of xn is Cauchy. That's some thick stroke right there. All right.
Yeah.
F of xn is Cauchy. So y, so let epsilon be positive. Then we know that x of n is Cauchy, right?
Uh-huh.
That's the thing, we spend so much time on it, so it's better be Cauchy.
Okay.
Therefore, there exists some rank n, such that for all p and q, which are bigger than n, we have that. So here what one I want. Okay, I want x p minus xq to be less or equal to epsilon over 4.
Okay.
Okay. And the 4 here come from the bound that we have already on f. Okay.
Okay.
By the previous, I guess we should. I mean, I guess I should have put it on in the lemma, but I guess we're gonna see that by the previous computation. We have f of xp minus f of xq is less or equal to 4 times the difference between xp and xq, right? That's the Lipschitz part that I told you. Okay. But now we know that xp minus xq is bounded by epsilon over 4. Therefore, this is 4 times. It's bounded by 4 times epsilon over 4, which is just epsilon. Therefore, xp and therefore f of xn is Cauchy. Okay.
Okay.
Okay, what else can we do now? Okay, maybe just to finish the proof because we're very close. So the same goes for y of n. The same goes. Y of n. Okay, now I need one simple thing. So, okay, I know that those two guys are x of n and y of n are bounded over 1 over 2n, right? So I will skip a little bit of detail, but this show that the difference between x of n and y of n is going to 0.
Okay.
I mean, you can sort of see because 1 over 2n is going to 0, therefore.
Yeah.
Yeah, I should put probably the difference. Okay, so which one is bigger? So y is bigger actually than x. Y of n is bigger than x. Okay, this guy. Okay, this is fine. Okay, what else do I need now? So I know that. Okay, I know that f of xn. Okay, I know that f of xn and f of yn are basically the same, converging to the same value because we have the difference here which is going to 0.
Yeah.
But now I need to use that to conclude that f of xn is going to 0.
Okay.
So the last part is to show. We want to show that f of xn is going to 0. Okay. So okay, I guess the thing that we want to show is that the difference between f of yn minus f of xn is going to 0.
Okay.
Because if we're able to do that, then we will be done because y of n, f of yn is always positive and f of xn is always negative.
Okay.
So the only way this can happen is because the two sequence has to go to 0.
Okay.
Okay, can we show that actually? Let's see. So, oh yeah, actually that's just follow from the Cauchy, from the Lipschitz properties. Okay, so we have this, right?
Mm-hmm.
Y of n is minus x of n is going to 0.
Mm-hmm.
So we also have that f of yn minus f of xn has to go to 0.
Mm-hmm.
So maybe here I can do this quick proof. So let epsilon be positive. Then there exists some rank. I mean, you started getting the picture. Such that for all n bigger than n, we have that yn minus xn minus well, I guess I just do this part is less or equal to epsilon over 4.
Mm-hmm.
So here I just use the fact that yn and xn are going minus yn minus xn is going to 0.
Okay.
And I will use the Lipschitz properties. So by Lipschitz, we have that f of yn minus f of xn is bounded by 4 times yn minus xn, right?
Mm-hmm.
But then this guy is bounded by epsilon over 4, so we have 4 times epsilon over 4, which is just epsilon. Therefore, f of yn minus f of xn going to 0. And now we get, okay, and now we have, okay, now we're very close. We just want to complete that f of xn is going to 0. Next. Yeah, now I'm kind of speed running the thing.
Mm-hmm.
F of xn is going to 0. And why is that? It's because f of xn is always negative and f of yn is always positive. This is from the construction we had of the sequence x of n and y of n.
Mm-hmm.
So what's gonna happen is we're gonna have that. Well, actually, I can probably I want to show that probably 0 for y. Okay, so what's gonna happen is we're gonna have that f of yn. Okay. So how the proof goes? You take an epsilon as usual. So you know there exists some rank n such that for all n which are bigger or equal to n, you have that the difference between f of yn minus f of xn is less than epsilon. Here.
Okay.
Here, remind the fact that I didn't use absolute value because I know that y is positive and x is negative.
Mm-hmm.
Therefore, there's no need for absolute value. Okay.
Okay.
And okay, using the fact that f of xn is a negative quantities,
Okay.
Mm-hmm.
That means that when I subtract by minus f of xn, I'm actually adding stuff, right?
Mm-hmm.
So this part here actually is adding stuff to my existing to this quantity. So using this fact, I have that f of yn is actually smaller or equal to epsilon. Okay, just because the fact that f of minus xn is a negative quantity and we are subtracting by it, so we get the thing on the red.
Mm-hmm.
This part is positive. Therefore, if I remove it, then it's even smaller.
Mm-hmm. Yeah.
And as f of yn is a positive quantity, then we also we get that f of yn is stuck between 0 and epsilon, which show that f of yn is converging to 0, which concludes the proof. And yeah, so just to summarize what we did today, we found two sequences, okay,
Mm-hmm.
of rational number, which are both Cauchy, and when we apply it to the function f, which is basically x squared minus 2,
Mm-hmm.
It will give you a 0.
Okay.
In other words, those sequences gonna solve the. I mean, they sort of solving the equation x squared is equal to 2.
Okay.
And what's cool about this proof is that using this fact that we just shown, that the f of xn is going to 0, or f of yn is going to 0, that's the same thing.
Mm-hmm.
We conclude that the sequence xn and yn cannot be convergent.
So xn and yn cannot be convergent.
Yeah. Because otherwise, xn would have to go to square root of 2, which is not a rational number. Therefore, you get so here you get kind of a nice example of a sequence which is Cauchy, but it's not convergent.
Okay.
And yeah, that pretty much show you like why some sequence can be Cauchy but not convergence. Usually, is because here you can see the problem is going on is that those sequences are sort of converging, but they're converging to square root of 2, which is not a rational number.
So, like for typically like Cauchy sequence, before we think of the real numbers, right?
Yeah.
They're supposed to be convergent, right?
Yeah, I mean at least morally they should be convergent.
But if there's like say another like set that basically is involved that we don't know about, but then we find that there are Cauchy sequences that are not convergent, then is it safe to basically say that there might be another set that we're not aware of in this thing that we're looking at? Like whether it be numbers or whether it be like statements or ideas or something like that? Is it safe to assume that?
So yeah, here you kind of get the idea is that the fact that those Cauchy sequences are not convergent means they're converging to a bigger space, right?
Yeah.
You can like add stuff to the rational to make those sequences converge.
Okay, so what we did was basically show that because it does involve the square root of 2 with these two with yn and xn, right?
Yeah.
So we use those two to basically we use like yn and xn to basically act as sort of like the measuring sticks of how close we get to the square root of 2, correct?
Yeah.
Okay.
So basically, I mean, you can sort of think of those sequences as the square root of 2.
Uh-huh.
If
It's just
you,
that
yeah.
we're just basically using them as sort of like a machine where it's like we're getting closer and closer and closer, but not touching it.
Yeah, exactly. There's like some point that they're not reachable for us, but we're able to like getting close together. Close to that.
Okay. So basically, the importance of Cauchy sequence is basically to, I guess, give us sort of an approximation of like how to get somewhere, whether it be numbers or whether it be like statements or whatever, right?
Yeah.
Okay.
And usually those are very cool Cauchy sequence because they're able to see like if your space is missing point.
Mm-hmm.
I mean, if you ever do like PDs I mean, maybe not the first course in PD because usually the first course is just computation, but
yeah, it's linear. It's mostly linear PDs.
But if you do like the theory of PD where you have to do a lot of analysis, there are some things similar that happen with the rational number, which happen with the differentiable function.
Mm-hmm.
So you can give a notion of distance for those function.
Mm-hmm.
For example, you can say that, I mean, you will give you will say that, for example, the difference between two functions will be the integral
Sascha,
of...
do you want to answer Goofy the Ultimate's question? They asked like, what is this on? Because we went through a lot.
So basically what we were trying to show is to find an example of a sequence of rational number. So right now, okay, maybe I will give you the full context. So right now we're building the real number from scratch. So we've been doing that for a few weeks. And right now I was showing you that the rational number are not complete. And what it means that there's Cauchy sequence in the rational which are not convergent. And I just gave a very concrete example with the square root of 2. So we build a sequence which approximates the square root of 2 with arbitrary precision. And we show that this sequence is Cauchy, but it cannot converge because otherwise, I mean, it would be the square root of 2, which is not a point in the rational numbers.
Mm-hmm.
And I was kind of giving you like so the thing we did here is kind of to build the real number.
Yeah.
But this construction is actually very useful for more complicated stuff like PDs or functional analysis in general. Mm-hmm. So if you have two functions, you can make sense of a distance sometimes. Like this is one example of the way you could define the distance. This is called the L2 distance. And you can start like with good function because usually when you do PD, you want the function to be differentiable or even smooth, right?
Yeah.
You don't want them to be like a mess, right? Because you want to be able to take derivative. And you may ask it on maybe one of the key point of convergence and Cauchy sequence is those definitions only involve the notion of distance, right? As long as you have a distance, you're able to make sense of what it means for a sequence to converge and also what it means for a sequence to be Cauchy. And if you take like nice function like smooth one, let's say, you will see that smooth function, which are very nice, those are the one you want to study, are actually like the rational number. They're missing function. There exists sequence of L2 function, of L2 smooth function, which are Cauchy, but does not converge to a smooth function. They the function get messed up and it's no longer smooth.
Does that also mean that they're not continuous?
Yeah, they can even not be continuous sometime.
So does that mean that they're discrete in that regard? Like basically, like since it's the rationals, it's gonna cut off at certain points.
So they can. So basically, I can give you an example of a sequence of function, which is. So maybe I will just do some drawing because I don't want to go over the detail.
Yeah.
But basically, what you can have is function that looks like that. They're like zero at every point.
Yeah.
Except at like some point where they have a peak.
Reminds me of quantum mechanics.
Yeah, they have a peak at y is equal to 1, okay? So this guy could be, for example, your first function. Yep. And what you can do is you can create a sequence of function where the base of the peak is getting smaller and smaller. So maybe
So maybe this is f of 2. And what you want is you want this peak to like go to 0, basically.
Right. Okay.
And for the integral, those functions would be like very close because the area under the curve is not that different. But when you take the limits of those functions, you will end up with something which is not continuous. You will end up with the function that jump. So it's going to be 0, and then at the origin it's going to jump to 1.
Okay.
And this is one example of them. So usually, if you take like nice smooth function, you don't get a nice function, and that's kind of a shame because the theory of sequence is very useful to find solution to PDEs. But so usually PDEs are usually reformulated in terms of variational problem, which does not involve derivation.
Goofy basically asked, is this similar to an example to the famous forming new decimal by ordering of every decimal from 1 to 0 and having sets of rules that differentiate from every other decimal by +1 or -1 because a digit has been altered. And then they also asked, using a limit here, I presume that you take the limit, but does that mean we have a dot? Our slope has been narrowed by a function, by using a limit would mean we wouldn't have that base.
Yeah, so for the sequence, maybe the base would be like something like 1/n. Like this guy would be like 1/n. And the idea is that every element in the sequence has like a good base, but when you take the limits, then this base go to 0 and you just end up with a dot.
Oh, okay.
So the function is equal to 0 every time except at the origin when it jump to 1.
Okay.
So this is one of the example. And the first part I was not exactly sure what he was talking about. It was sound like a type of Cantor argument to show that the real numbers are not countable, but I'm not sure it's what it meant to write, but yeah. And so usually to have solution to PDEs, usually people want to use analysis. They want to have like sequence of smooth function that converge to something.
Yeah.
I mean, that's at least like how we prove like the most basic PDE. I mean, basic in quotation mark because it took like 200 years to be able to show existence of solution for them. But that's beside the point. We usually want like stuff like a sequence of function, and I mean, using stuff from analysis to be able to find the solution. But then we sort of get into trouble because you cannot do good analysis with smooth function because they're like space with missing points. Therefore, we had to add function to the space of smooth function, and then you get to stuff like weak differentiable function, or what's the name of the other? Wait, what was the? Wait, I forgot the name of when you complete with the L2. Is the sub-LF space.
Oh, okay.
And stuff like that. And then you sort of have a funny thing which we have a non-smooth function, which is a solution to a PDE. But it has to, I mean, you have to make sense of what it means, so it's a weak sense of a solution.
Yeah, Goofy the Ultimate basically says Cantor's diagonal argument.
Yeah. Okay, that's the thing I was. Yeah. That's an argument that you can show that for real number are not countable.
So basically, the whole entire lecture for today was basically showing that Cauchy sequences, a lot like when they are used to actually help us to see that there might be more than what we have. Yeah. In other words, like for the rationals, we realize that there's more beyond them, and yet Cauchy sequences that do not converge basically shows that there's more sets of whatever it is that we're dealing with, whether it be numbers or mathematical statements, correct?
Yeah, so we're missing like points, yeah.
Okay.
And that's so I mean, we will not do that in general, but if you have a metric space and you don't have all the Cauchy sequences are converging, then you can build the completion of that space.
Okay. So
which
we
is
did
like
2 days of Cauchy sequences, and now
Yeah.
I feel like I know a little bit more about them, and I never realized how powerful they are. That's mind blowing, actually.
Yeah, I mean they're kind of cool. Yeah, you will see they are very useful when we talk about series, because as I mentioned, Cauchy sequence has the very cool properties is that you don't need to know where they converge, right?
Yeah, and it's funny because we haven't done that much with say epsilon and delta limits,
Yeah.
and it feels as if we're already dipping our toes into something that's much bigger than that.
Yeah. I mean,
Go on.
completion of metric space is kind of a big concept that you have to learn at some point. But I mean, we kind of did the one case which is going from Q to the real number, but you can do it. It works for every metric space. You can always build the completion.
Oh, okay. Okay, Sascha. What are we gonna go over next week?
So I guess next week we should probably start splitting. Maybe we could start the linear algebra and finish the construction of the real number for the analysis course.
Okay.
So I guess for real analysis, I'm gonna use. So today I give you a choice. I ask you if you wanted to do something more concrete, I mean, showing that sequence converge like we did, or if you wanted to if you wanted to end the construction of the real number and you choose the more concrete way. So next time we're gonna finalize the construction of the real number.
Okay.
Using a quotient ideal and stuff like that.
Okay.
Also, I also want to point out that at the beginning I showed you a very simple algorithm that's able to compute the square root of 2, and it took over an hour to prove that this algorithm actually gives you the.
Yeah, it's it's a lot. Yeah, it's a lot. I think this is why mathematicians love computers, and now I think this is why they're loving AI, because it makes the proof writing and probably the proof, I guess, scratch work much easier, because they see how it's supposed to behave in some ways.
Yeah, but basically, I guess you can test it, but also every single algorithm, iterative algorithm like we did, there's always the algorithm took 5 minutes to write, but it takes much more time proving the correctness of it.
Okay. All right, Sascha, once again, thank you for another awesome and informative lecture. Is there anything you want to say to our global audience before we finish off today's stream?
So drop the bell, drop the subscribe, drop the follow, join the Discord. I guess sub on YouTube.
Yeah.
Do you have other stuff?
Yeah, I will put it up. So
Alright.
This is my YouTube channel, guys, MathSpellBook. In addition to my Discord, if you're in Twitch chat. In addition, you can also follow me on my video game channel, Uncle Talks. That's where I play video games. I will be streaming on that channel tonight if you want to catch that. But if you're watching this on YouTube, all the links will be in the description down below. In addition, if you want to have a nice discussion between two people that love math, talk about math, or you just need something to be productive for your math or physics journey, or just a productive stream you need, just consider subscribing to the MathSpellBook channel. Okay, let me take a look. And also, thank you for actually writing that, Sascha. Because now I can actually follow you through my MathSpellBook channel. So that way, if you do decide to stream, that way I can catch up with you.
You're welcome, Goofy. I hope you had a good time with us.
Yeah. Hopefully you had a good time. Actually, Goofy, you might teach me a thing or two as well about math, because it seems like you know a lot of math as well. I have no experience with mathematical proofs, so I'm learning more from Sascha every single stream. Or every time we talk, I learn a lot more from this guy all the time. Let's see, is there anyone streaming math content on Twitch? Maybe we can give them a raid. Let me see here. Let me just take a look. Is anyone... Oh, Academy is streaming. We'll give Academy... We'll give Academy a raid. Proofs are so interesting. Yeah, I agree. They are interesting. They're pretty complex, and like luckily I'm recording these lectures that Sascha is so nice to basically provide for us. So I will upload these on YouTube, like if we experience too many like cottages from my internet. So yeah, be prepared for those. So we'll begin the raid into Academy of Useless Ideas stream. So ideas, there we go. I like my most favorite sort of proof was light takes the shortest path of least action. Oh, that's cool. I haven't gotten to that level yet. I'm still trying to do basic physics right now. Alright, the raid has begun. Once again, Sascha, I will see you next week or whenever you may be in the Discord server. Thanks again for teaching us. Take care of yourself.
Take care, man.
Alright guys, we will commence the raid, and always remember, everyone is precious, you guys are just as precious as everyone else, and I will see you guys in the next stream next week. So take care guys, bye-bye.